Okay, so welcome to the exercise class. So today, the main topic that we're going to talk about is going to be in the noisy operations. So we'll look at the sets of classical noisy operations and quantum noisy operations, and we'll try to, to characterize them somehow. And this will connect to the lecture as well. So why are we interested in noisy operations? So essentially in the lecture, we started to discuss the topic of resource theories. And these resource theories are usually defined by a set, so-called a set of operations which are considered free. So we need to define a set of operations which we can do for free in this series. And then given this set of operations and maybe given some resource, we just see what exactly we can kind of take out of this resource. And so the examples of these are the resource theory of local operations and classical communication, which is essentially a resource theory of entanglement, because the only operations that you can perform for free are non-entangling operations, at least globally. Or, for example, in the case of like quantum computational resource theories, one can also, for example, restrict the operations to just stabilizer operations. But the theory we'll be looking at today is the resource theory of informational non-equilibrium. So let me explain in a moment why it is information non-equilibrium. So in this resource theory, one can do the following things. So one can perform unitaries on a system. So any unitary can be performed. Then one can prepare a system in a uniform quantum state. So prepare maximally mixed states. And finally, one can take partial trace over any subsystem of a system. And so we see that, for example, if we have these this set of allowed operations, and for example, if we only restrict ourselves to these operations and assume that we don't have any additional resources, this essentially means that we only possess maximally mixed states, and performing any unitary on this set of this maximally mixed states would give you again back this set of mixed states. And the same with a partial trace. If you take a partial trace of a maximally mixed state over any subsystem, of course, given that kind of you fix this division into subsystems, you will get also a maximally mixed state. And then the most general form all these three operations can be expressed in is so-called noisy operation. And again, as I said, applying this noisy operation to maximally mixed state would result in a maximally mixed state. So any state which is not uniform, so which is kind of doesn't have this informational equilibrium over all its degrees of freedom, essentially will result potentially not in a mixed state, so it could be used as a resource, and hence this theory is called a resource theory of this informational non-equilibrium, because only non maximally mixed states actually result in not arriving back to this set of this maximally mixed states. And the general form of this noisy operation goes as follows. So first, we have the ancilla, which is prepared in a maximally mixed state, which is allowed. Then it is adjoined to the system of interest. So our resource. Then it is coupled to it unitarily. So it just means that we perform a join unitary on the system and the ancilla. And then finally, we take the partial trace over some subsystem, not necessarily the ancilla system. Okay, and as I said again, any non-uniform system serves as a resource. And what we would like to understand is what is exactly the set of this noisy operations. So, and for this, we will look at two cases. So first, we'll look at the set of the classical noisy operations, where the structure of a set is quite simple. And yeah, we'll go through how to show the structure. And then we will look at the case of the quantum noisy operations, which is not as straightforward. So let me start with the classical noisy operations. And the idea here is that there are two other sets of operations that we would like to compare this operation to. So the first is so-called unital operations. And I will give all the formal definitions just in a moment. And the unital operations are basically the operations which, if they're given uniform probability distribution, then they also spit out the uniform probability distribution. And the third set is the set of the operations which can be expressed as mixtures of permutations. And we'll see in a moment that actually for classical noisy operations, all of these three sets are the same. To prove this formally, let us first define what a classical noisy operation is. So a classical noisy operation is essentially the operation D, which maps from the space V in to V out. And V in and V out can be seen as some representations of a physical spaces or spaces of physical states, but essentially one can also understand them as just probability distributions in with the dimensions corresponding to these vector spaces dimensions. As in, so the dimension of the first is D in and the dimension of the second is D out. And this is a map which is positivity preserving and also normalization preserving. So this is just to ensure that it indeed maps the probability distribution to a probability distribution. Then the action of this map D on the incoming state could be described as the following: sum over omega A prime pi of x in tensor product MA. So the idea here is that we also consider that there exists an ancilla with discrete physical space, which has this physical state, omega A, and also exists a permutation pi on omega n, omega A, with the induced representation on the vector spaces V of omega n tensor product V of omega A. And so what happens in this definition is exactly what I just explained before. So first, we couple the system to the ancilla, which is in uniform. State. So it is essentially a uniform distribution. So we just have our incoming distribution. We combine it with the ancilla, which is in the uniform distribution. Then we perform a permutation on this joint system, and then we just trace out, or we sum over a sum subsystem, which we here label as A prime, which is just a complement to the system corresponding to omega out. So formally, this corresponds to this.
Can I have a question?
Yes.
What do you mean by induced representation?
So essentially, what we are doing here is we have some physical states in this space omega A, right? And then for each state, we have this vector of probabilities, which is expressed in this V of omega in, for example. And then the permutation itself happens in the space of omega n by omega A, but but pi, it is its induced representation when we express these states as probability vectors in V.
Okay, thanks.
Okay. Okay, so this is classical noisy operation. Then the other operation is, yeah, I think I made a small mistake here. So for classical noisy operation, this is called uniform preserving. So uniform preserving operations are the operations which map the uniform distribution to a uniform distribution. And so if we see, of course, all of these maps can be expressed as just matrices, which act on the vector in V in and spit out the vector in V out. And this this property of this matrix, which just maps the the uniform distribution to uniform distribution, but just of a different dimension. And since it also has to preserve the norm, as it has to map the probability distribution to a probability distribution, it must have the following properties. So first is due to normalization. So its columns have to sum up to 1. So this is just due to normalization. And also because it maps uniform distribution to uniform distribution, essentially we can write that we act on the incoming uniform distribution, and then we get the outcoming uniform distribution. I'm just leaving the indices here, so this would still be understandable. But yeah, here we're just acting with this matrix on the column of vector on the column vector with all the same entries, which is 1 over d in. And from here we actually get that sum over j dij equals just d in over d out. So we see that the uniform preserving stochastic maps, which are expressed in terms of these matrices, have these two properties. Moreover, in a case when the input and the output dimension are the same, you're already seeing these matrices because these properties just reduce to the sums over columns and rows being equal to 1. And so these are just doubly stochastic matrices.
Can you go back really quick?
Mm-hmm.
Okay, I just wanted to look at the expression again.
Yeah, sure. Okay, and so now what we will want to understand is whether these two classes are the same matrices. So for this, we need to prove two things. So first, we need to prove that all classical noisy operations are uniform preserving. And we need to prove that all uniform preserving operations can be written down as classical noisy operations. Okay, so first, so noisy operation, uniform preserving. Okay, so this is fairly easy because, again, coming back to our definition, if the incoming state is, if the input is uniform, then essentially, and when we couple it to the ancilla, which is also a uniform state, we also get a uniform state. So this is all uniform state. And no matter how we permute this uniform state, we'll still get a uniform state. So this is also uniform. And then whatever subsystem we trace out of this uniform state, we'll still get a uniform state. So inputting the uniform state, we output the uniform state. So hence, for every noisy classical operation is uniform preserving. Perfect. So now the other direction, which is a bit more tricky. So suppose that we are given a uniform preserving operation, and we want to see if it's a noisy operation. So first, we'll start with considering an easier clause. So we start with considering the case when the dimensions of the input and the output are the same. So if the dimension of the input is the same as the dimension of the output, then we just shown that for this case, the uniform preserving map is actually a doubly stochastic map. So D is doubly stochastic. This is very useful for us because here we can just use Birkhoff's theorem, which says that any doubly stochastic map can be represented as a mixture of permutations. So for some set of permutations pi and some probability distribution small pi, we will get that D equals sum over I, pi, pi. So this is due to Birkhoff theorem. So now our aim is just to construct such an ancilla and such a permutation that somehow the action of our matrix would correspond to one big permutation on the system and ancilla. Okay, so and the idea how to construct this is the following. And actually, the same idea will come up when you consider the similar proof, but for quantum operations, for quantum noisy operations. So first we prepare an ancilla which can be arbitrarily large. And we prepare it, of course, in uniform state because that's the only thing we can do. But we also keep in mind that we prepare it large such that we can partition it into sample spaces. We partition its sample space into subsets of relative sizes pi, which correspond to the probability pi here. Partition into subsets with relative sizes pi. So, for example, what would that mean is that, for example, if the ancilla is of the dimension D, then the dimension of the first subset would be P1D, dimension of the second would be P2D, and so on. So maybe I just... Yeah, however many there are in this probability distribution. Yes, so we partition it into these subsets, and then the operation that we apply is the following. So we apply a controlled operation. If the ancilla is found in the subset I, then the corresponding permutation pi is applied on the system. So essentially, such control permutation is itself also a permutation on the system and the ancilla. So this and so then this permutation gives us exactly the action of the map D, but also it it suits the definition of the classical noisy operation. Or at least like this permutation pi on the joint system of the input state and the ancilla in the uniform state. And then finally, we discard ancilla. Okay, so I will not like carry out the full derivation of this here because this is part of your exercise. So I'll leave that part to you. But this is essentially the controlled operation that one has to carry out to show that uniform preserving map D is a noisy classical operation. We are not, however, done yet because we only consider the case when the dimension of the input state is equal to the dimension of the output state. Now we need to consider the case when they're not equal. So here, as you might already guess, the way to construct this new operation is to somehow reduce it to the operation that we already constructed by equating the dimensions of these two systems by adding ancillas in the uniform state. So that's exactly what we do. So we add ancillas with the dimensions d1 and d2 such that they just complement the dimensions of the input state and the output state. And we also consider a matrix D0, which is a matrix of the size D1 by D2. And suppose that all entries of this matrix are 1 over D2. So essentially, yeah. So D2, D1, 1 over D2, so on, 1 over D2, and so on, so on. And what is essentially a D0? It is a stochastic matrix. All entries non-zero. The columns sum up to 1, so it maps a probability distribution to a probability distribution. But it also has a property that it maps every state of dimension D1 to a uniform state of the dimension D2. So whatever state of the dimension D1 we take, it's gonna map it to a uniform state of dimension D2. Since it maps every state to uniform state, it must be uniform preserving. So D0 is uniform preserving because since it maps every state, it also maps a uniform state to a uniform state. Which means that D by D0, and we're coming from the assumption here that D is uniform preserving, D by D0, tensor product D0, is also uniform preserving. Moreover, it is doubly stochastic because it maps the state of the dimension d in by d1 to the state of the dimension of d out by d2, which are equal. Okay, we're back to our doubly stochastic matrices, which we love because we can apply the Birkhoff theorem. So we can express it as a mixture of permutations. And so now we can just kind of repeating the previous case, do this, do the same thing as in. So first we, okay, maybe let me recap first. So we have this D tensor product D0, which is a mixture of permutations, and we just shown that we can express like mixing the mixtures of permutations as a classical noisy operation. And now, like, to start from the beginning, from the input state, we essentially have to recap the operations that we applied and see whether they're all noisy or not. And if they all are, then we kind of win. So essentially, the protocol goes as follows. So first we adjoint the system to a uniform state of the dimension d1, which is allowed. Second, and it is allowed, and it is a noisy operation. So second, we applied the mixture of permutations, which is also an allowed noisy operation, as we've just shown in the case where d in equals d out. And third, we just marginalize or trace out over the system of the dimension d2. So let me make this in green. So this is noisy, this is noisy, this is also noisy. Marginalization is allowed, adding ancillas is allowed, mixture of permutations are allowed. So this is all noisy, and we win. So what we've just shown is the following. So to recap, we first showed that every noisy operation is uniform preserving, and then we shown that every uniform preserving operations is noisy, which means that these two classes coincide. Moreover, in the case when the input dimension equals the output dimension, such an operation can be expressed as a mixture of permutations. So all in all, we have that classical noisy operations and uniform preserving operations are the same. Okay, everything is great in the classical case, none problems, quite clear. Okay, so there is a question in the chat. In the initial part addition of the Hilbert space, are all pi either pi or integers, or are we considering some non-integer dimensional space of the dimension pi d? Okay, very good question. It's a bit of a subtle point. So when we are performing our partition into subsets of the ancilla space with a relative size as pi, we can always choose an ancilla of an arbitrary large size. So we always choose the size such that all PIDs are integers. Of course, the subtle point is that maybe we're not always allowed to do so. Like, for example, when PIs can be irrational. Two arguments against this. So one, the first one is more mathematical, which says, okay, even if we kind of allow for a small for a small error in how we define our subsets, then it will just induce a small error in how the matrix D is decomposed. But this is kind of robust, so we can make this error as small as possible, increasing the dimension of the ancilla. A more physical argument of why this cannot happen is, well, simply because kind of physically, if we measure something or if we calculate some probability, we always write it as as a finite number, in a sense of like as a finite decimal number. So yes, there is always there can be an error, but motivated physically, you probably can always find D large enough so that error would be arbitrarily small. Does this answer the question? Okay, I'm glad. So now coming to the quantum case, since we're kind of trying to understand quantum mechanics, of course there are analogs of all of these definitions all these notions I was just telling you about in the quantum case. So for example, there are quantum noisy operations, which essentially are exactly the same as classical noisy operations, but you just insert quantum states instead of probability distributions. So we have this operation epsilon, which is a trace preserving completely positive map, which acts on the incoming state rho in. And the action is follows. Maybe I'll write trace later. So first we couple it to the maximally mixed state of some dimension A and Silva. Then we perform some unitary, and then we trace out some subsystem, which we call A prime. And A prime is the dimension of the complement Hilbert space, which is defined by Hilbert spaces of the incoming and outcoming state. So this is rho out. Okay, so these are the quantum noisy operations. Also, there is an analog of the uniform preserving operations, which is so-called unito operations. And here, instead of mapping a uniform distribution to uniform distribution, we have mapping of maximally mixed state to a maximally mixed state. So we have the incoming state, which is maximally mixed, and then the outcoming state is also maximally mixed. And there are following inclusions that we can prove, but it turns out that these two sets are do not coincide as they do in a classical case. So for example, noisy quantum operations, quantum noisy operations. So quantum noisy operations, they belong to the set of unito operations. So you can prove that every quantum noisy operation is unitol. Another thing that we can prove is that mixture of unitaries also is a noisy operation. So both of these things you have to prove in the exercise sheet. And here for the second, so the first inclusion is quite straightforward. Like, I guess you can see it here that even if you just think about how you plug in instead of row in maximum mixed state. The second inclusion, we already actually seen the proof of it. So the hint here is to look at the classical case and how you have to partition the space. And so essentially we have the following string of inclusions, as in the mixture of unitaries belongs to the set of noisy quantum operations, which in its turn belongs to the class of unital operations. But these two inclusions are strict. So there actually has been shown that there exists noisy quantum operation, which is not a mixture of unitaries. And also there exist unital operations, which are not noisy quantum operations. Yeah, so these examples are quite involved. So I just left the references in the exercise sheet if someone is interested to see how one can prove that these inclusions are not are strict. Okay, so this was the part about noisy operations. To comment on two other exercises in the exercise sheet. The first exercise, they are both much more trivial. The first exercise concerns, the first exercise concerns the Lorentz curves and how we can use them. And actually, it was also a revelation for me that Lorentz curves were not invented to be used to illustrate majorization concept, but they were actually invented to showcase how equal the economy of a country is. So yeah, you can look it up. It's quite interesting. And another exercise concerns the heat capacity of the system, and also how this heat capacity scales if you couple n systems in a thermal state. Okay, I think I'm out of time, so this is it for today. If you have any questions, please shoot.